Hello. Somebody just dropped out. Oh, interesting. Okay. Yeah, so if you guys have questions, you could either type them in the chat or you could just say them. That's also fine. Can you hear me, by the way?
Yeah, we can hear you.
You can hear me. Yay. Okay. Number 13. I'm just going to write these down. That's a good idea. Writing them down, imagine that. 81, 11, 23, 16, 4, 10, 16, 25, 27, 4, 10, 16, 25, 27, 34, 37, 'What has happened to my pen? Is it not working? That's not useful. Oh, yes, it is. Okay. Here we go. Okay, 50, 52, 56, 66, 72, 75, 16 from the 5 steps one. Okay, 16, 5 steps. Okay. And let's see what else we got here. Scroll down. 50, 30, 50, 6, 30. 64. Works better if I write with a pen and not my stylus. 64, 73, 74, 83. Okay. 87 and 94, 87 to 94, 18, 29. Okay. No, I don't want a keyboard, thank you. Okay. Hello. 86. All right, I'm going to get started and you're going to let me know if you are satisfied after an explanation or not. If you're if you are, you can just like not do anything, but if you aren't, you can let me know. And if you come across a question that I've skipped by accident or something like that, you can let me know on that as well. Okay, number 4, you do not need to do. It is in gray, and so you do not need to do it. We will be doing that after we have done equilibrium. Okay, so don't worry about number 4. Omit. Number 13, no, 11 and then 13. 11. Here we have an electrolytic cell. So which one of the following statements is true regarding the movement of the particles? So we have our positive terminal of our battery up there and our negative terminal of our battery up there. And of course, electrons are repelled by negative. So because they're negative, so they're moving that way and they're attracted to positive. And electrons always flow in alphabetical order from the anode to the cathode. A to C. So that means that our anode is the nickel. So that's our anode. This is our cathode. And the reason a cathode is called a cathode is because cations migrate towards it. That's actually why it gets its name. So cations migrate towards the cathode, and anions towards the anode, and that's how the anode got its name. And so we would need to have our cathode is the iron, so the nickel 2+ ions will move towards the iron electrode. Why doesn't iron get oxidized? That is because this is an electrolytic cell and we are pumping electrons into it because we've got a battery. Yes, and it's got a positive terminal and a negative terminal. We are actually forcing electrons to go this way. So if we are forcing electrons into the iron, it's really hard for it to lose an electron. Yes? And that's what electrolytic cells do. They can work against what would naturally happen. Did that make sense? I could certainly go over number 10, yes. Oh, yeah, and I forgot number 10. Excellent. Okay, how are we feeling about number 11? We're good? No one's saying no, so I'm going to assume yes. So number 10, again, we have an electrolytic cell. And when we have an electrolytic cell, that means it is non-spontaneous, non-spont. And so we have to have a power supply of some kind or a battery, power supply or battery. And here is our battery up here. We have our negative. Oh, okay. This one isn't even asking us anything about that. It is asking us if the battery symbol with the positives and negatives wasn't included for number 11, you wouldn't know. You couldn't tell. You have to be given that. Okay. So you will either be given a negative positive, and probably they will label it for you, but I assume at this point most of you know that the big one is positive and the little one's negative. Or the other thing you could be given is you could be given a little box that looks like this and it says DC, and then you would have a positive end and a negative end. And what that is it represents a power supply that you plug into the wall. And the power coming out of your wall is alternating current. So the electrons go like back, forth, like sort of like wibble, wobble, wibble, wobble. DC, direct current, travels in one direction. And in order to have an electrolytic cell, we need to have the electrons traveling in one direction in a circle. We can't have them dancing like back and forth like that. That's just not cool, okay? So if they write DC, that just means that it's acting like a battery, but you can set it to whatever voltage you want. And this one, silly me, doesn't even care that it's an electrolytic cell or an electro anything cell. We're just looking for the anion, and an anion is an ion that has a negative charge. So boom, there we go. Huh. I was thinking way too hard about that one. All right, that was number 10. We're going to move on, unless we have questions about that, to number 13. Okay, so what is the change in oxidation number when pitch blend reacts with nitric acid to form la 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 la? Okay, so we need, if we want our change in oxidation number, we need our oxidation number final minus our oxidation number initial. So our final, it reacts with nitric acid to form. So this is going to be our final state. This is going to be our initial state. And I am not good enough that I can do that in my head. So I am going to write out UO2, NO3, 2. That's my final state. And I have a U, which is the thing I don't know. I have 2 oxygens. And this group right here is nitrate. And because it is a polyatomic ion, you can treat polyatomics as a group and just use their charge like you normally would. And this whole thing has an overall charge of 0. So I have 1 U, 2 oxygens, 2 nitrates equals 0. So 1 U plus the oxidation number of oxygen is -2. The oxidation number of nitrate as a group, remember nitrate is just -1, equals 0. So I get U -4 -2 equals 0. And so U is equal to +6. So that's my final. +6 minus my initial, this one should be a little easier. I've got 3 U's and I've got 8 oxygens is 0 again. There's no charge up here, so it's 0. And so that's plus -60 equals 0. Write 0 so it doesn't look like an oxygen. 3U. And then 3U is equal to +16. And so U is equal to +16 over 3. So we are changing from +16 over 3 to +6. Am I doing that right? It must be. Okay. And so this would be 18 over 3. Yes. Minus 16 over 3 is equal to 2 over 3. So that's going to be +2/3. A little bit of a nasty there. One of the things to remember is that if you have a polyatomic ion, you can just treat it as a group, so you don't have to worry about what's the oxidation state of nitrogen. Oh my God, I don't know. No, there is no rule for nitrogen. Nitrogen can be different things in different circumstances, unlike, say, oxygen, which is only very rarely not -2. Okay, that was number 13. And I assume that you guys will type into the chat if you have any other questions or just talk to me. Number 16 is next. Which of the following skeleton half reactions are not oxidations? So we are going from ClO3 to ClO2. Since the charges are remaining the same, we've actually lost oxygens. And if the charges remain the same and we don't have as many oxygens, that is not oxidation. Oxidation is when you put oxygens onto something. It's like a little cheaty way of doing it, yes, rather than calculating out all the oxidation numbers. Put oxygens on. Whereas here we have taken oxygens off. If you wanted to, you could find the oxidation number. We have ClO3 minus. Oxygen is -2, so that's -6. We already have a 1 there. So that's negative, that's going to be +5. ClO2 minus, that would be -4, of which we just have 1 left over, so that would be +3. And so that went from a bigger number to a smaller number, so the oxidation number was reduced. When the oxidation number gets smaller, it has been reduced. Okay, in my second one, Oxidation, I put oxygens on. Reduction, if I put hydrogens on, if I'm changing the number of hydrogens, and I can do that here because I've got the same number of carbons and I have the same charge, so I'm comparing apples to apples and not apples to oranges. If you put hydrogen on, that is reduction. So reduction is putting, oops, hydrogen on. So in this case, we've put some hydrogen on here. We've got 2 more hydrogens here than we do here. And so that is a reduction. So here we had a reduction. And here we have a reduction. And again, if you want to, you can do it by finding oxidation numbers. Instead, you have carbon, 2 carbons, 4 hydrogens. Oxidation number of hydrogen is +1. So we have 2 carbons plus 2, no, not 2, 4 plus 4 equals 0, which gives us 2 carbons equals -4. So carbon is equal to -2. So we go from carbon having -2, and if we do the same math for this one, we end up with carbon equaling -3. Did anyone want to see that? Oh, this is really weird. Which are not oxidations. Oh, not oxidations. Oh my goodness. Hopefully they don't ask many of those stupid negative questions on the test. So number 1 is not an oxidation. It is a reduction. So this is not oxidation. Number 2 is not oxidation. It was reduction. And number 3, we are going from having 1 N to 2 O's to having 2 N's to 4 O's. So the ratio of N to O is the same. And so this is neither oxidation nor reduction. It is also not oxidation. So the answer would be D, 1, 2, and 3, because we've got reduction, reduction, and then neither. I hate it when they have those negatives in there. It messes me around. Okay, that takes care of 16. We're going to go to 18. Which of the following statements is incorrect? Incorrect. Given the following equation for the reaction that occurs when copper is dissolved in nitric acid. So is copper being oxidized? The oxidation number went up. Therefore, yes, it was oxidized. So this is a correct statement, which means that it's not what we want because we want the incorrect one. The product of oxidation is NO. That makes no sense because we just determined that copper was being oxidized. So I'm going to say that that one's probably the one that's probably wrong. So I'm going to circle that tentatively and just go back and check afterwards. The reducing agent is metallic copper. Reducing agents are oxidized. Oh, look, it got oxidized. So that is our reducing agent gets oxidized. I know it's the reverse of what one might think, but. And then hydrogen's oxidation number hasn't changed. It's +1. When you have hydrogen in a compound, it's always going to be plus, unless you have a hydride, but you'll never have those. So don't worry about that. So yeah, it is B. 18. Now we're into the 20s. 23. Okay, so we are using this information here. Oh, pen not working. Stylus, wake up. Let's try another one. Just going to pop a new battery in. Hopefully that will solve the problem. Come on. Sorry, I have to unscrew this thing and then get it back on. Oh yeah, and I could go over 19 for sure. Just grab a new battery here. Hopefully that's working. Okay, there we go. Okay, so I'll do number 23 and then I'll pop back to 19. As long as I can get a working pen here. Come on. Yay, okay. So we have an electrochemical cell. So we have zinc in zinc and nickel in nickel. A salt bridge connects the two half cells. So we have zinc and we have nickel. Which of the following statements is correct if 0.5 moles of electrons flow in the cell? So if we have 0.5 moles of electrons, we of course here have zinc 2+ in our beaker, and we have nickel 2+ in our beaker. We need to figure out who is the cathode and who is the anode. So we will jump over to our data booklet and we will look for nickel, which is here, and zinc, which is here. So whichever one is higher up is your cathode, and it's going to go forward. So nickel is gaining electrons and becoming nickel solid. So it's going to gain in mass. And whichever one is lower is going to be the anode in an electrochemical cell. And so it's going this way, backwards. And we will end up losing mass on zinc. So let's go back to our question. So nickel gains. Come on, there we go. Nickel gains. It's the cathode. Zinc loses mass, because it is the anode. And so we are looking at either C or D, which I might have predicted because, you know, there's two that could possibly be. And now we're going to look at the half reaction for nickel. So we have nickel 2+ plus 2 electrons goes to nickel solid. So there are 2 electrons for every 1 nickel. So if we have 0.5 moles of electrons, there are there's 1 nickel 2+ for every 2 electrons. And the molar mass of nickel, grab a data booklet here, is 58.7. 58.7. Okay. So this is not an AP question, so you can use your calculator for this. So 0.5 divided by 2 times 58.7, that's grams per mole. Grams per mole. And we get 14.7. So that's going to be C. Oh yeah, 19 is gray. So yeah, we don't need to do the ones that are in gray. Good catch on that one. All right, so 23 is done. We're going to go to 27. 27. Which of the species could be a product when we have NO2 acting as an oxidizing agent? If you are acting as an oxidizing agent, you are being reduced. So we need NO2 to get reduced. So we need N to have less oxygens, because if it had more oxygens, it would be getting oxidized. So we need N to have less oxygens. And that means that A is the correct answer, because it's only got 1 oxygen for every 1 N, whereas NO2 has 2 oxygen for every 1 N. And of course, like I said, you could do this showing oxidation numbers. So you could have N plus 2O equals 0. And then you would have N plus -4 equals 0. And you edit n equals +4. And then NO, n plus O equals 0. N minus 2 equals 0. N is equal to +2. So we went from +4 to +2, and so that was reduced. Okay, and you could do the same thing for all of the others, but like I said, if you know that, like in this case, you've got 2.5 oxygen to every 1 nitrogen. Here you have 3 oxygen to every nitrogen. Yes, there's a negative charge, but that's not, it's just a 1 negative, so that's not enough to make much of a difference. And in this one, we have 2 oxygen to every 1 nitrogen. So you can kind of look at it as like a ratio thing. If the ratios are the same, there's been no oxidation reduction. Yeah. Is that good? 320, that was 27. Ooh, 29. Which of the following would be best to make a container in which to store aqueous copper 2 sulfate? So we have Cu 2+ ions. And when they ask you what could you make a container of, you want to not have a spontaneous reaction. No spontaneous reaction, because otherwise, if it's spontaneous, the copper 2+ will react with the metal. So let's go find something that copper 2+ will not react spontaneously with. Where is our copper? Up a little bit. There's our copper. Now we have a whole bunch of coppers on here. Really, this copper here is the only one that you need to worry about. Okay. And the reason that is because it has a cell potential, or sorry, an oxidation potential rather. Oxidation potential? Reduction potential. Has a reduction potential of 0.34. So that is better than copper 2+ turning into copper 1. So if we've got copper 2+, we're going to choose the 0.34 because that is a better oxidation or reduction potential than copper 2+ going to copper 1. So who is spontaneously reacting with, or who is not spontaneously reacting with copper 2+? So we are looking for something that is higher up here. And I think silver was one of our options. Remember, if we've got that, we have, that is a non-spontaneous reaction. If you did not have a chart like this, which you will have this chart for the test on Friday, but on the AP exam, you won't have it. But what they could do is they could say, give you Cu2+, the oxidation potential, they could give you plus 0.34, and they could give you silver plus, and the oxidation potential is plus 0.80. And you can say, oh, for that thing to be going backwards would be negative 0.80. And then if we had that one, it would be 0.80, negative 0.80 plus 0.34. And I feel like I'm just rambling now. So are we feeling okay about that question? Even though I've rambled? You can always do the calculation to find the cell potential. I have done it in a non-standard way, but oh well. Okay. Let's see. That was number 20. Oh, I need to go back to the other one. There we go. That was number 29. Moving on to number 30. Where are we at? Oh, come on. There we go. Closer, 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 closer. 30. If the E naught for the half reaction were set at 0 volts, so that's for nickel, what would be the E naught for the half reaction for this one? So these are both E naught of reduction. So we need to go to our chart and look up nickel and copper. So we have copper. Nickel is, let's get rid of some of this. Oh, I'm not getting rid of this. Okay, so nickel is here. And copper is here. And if we set, did it say copper to 0 or nickel to 0? If we set nickel to 0, so if we set this, if instead of this being 0.34, if we moved our 0, normally hydrogen is set as 0, but really you could set it to anything. They just picked hydrogen randomly. So if we put 0.00 here, well, the difference between these two, we have 0.34 and we have 0.26. And if we add the two of those, 0.34 plus 0.26, yes, I'm using my calculator because my brain is just not that functioning today. And so we get 0.6 is the difference between those two. So if this was at 0 volts, then this guy down here would be negative 0.60 volts. Is good? Okay. $30, $34, I think is our next one. Oh, I missed question 6 way back. We'll come back to it at the end. I don't want to scroll all the way back.
Miss Fez?
Yeah.
For question 30, does it say that nickel is at 0? But I think you made copper at 0 on the chart.
Oh. Hang on. No, it says if nickel was set at 0. Did I write it wrong? Let's see. Oh, yeah, I wrote it wrong. Okay, so if nickel were set at 0, thank you. If nickel were set at 0, then this would be positive 0.60 volts. There we go. Okay, so sorry. Thank you for catching that, Ahmed. All right, so that would be positive 0.60. Okay, 34. So we are looking at the diagram up here because this diagram is for 33 and 34. And this is one of those non-standard electrochemical cells. So instead of having 2 beakers with a salt bridge, we have a porous cup, which allows the transfer of ions from one to the other. Okay, so which of the following actions takes place during the operation of the above cell? So we need to know who is the cathode and who is the anode. Copper and zinc, I happen to know because that's the one we do all the time, that copper is the cathode and zinc is the anode. But if you didn't know that because you haven't done it for 30 years, you could be like, okay, I'm going to look up copper and zinc. There's zinc way down there. And so in order for this to be spontaneous, because it's an electrochemical cell, we have copper, zinc. So this is going to be getting reduced, gaining electrons. And so that's going to be our cathode. And this one's getting oxidized. So that's going to be our anode. So that's how you know that copper is the cathode and zinc is the anode. So are zinc ions produced at the zinc electrode? Well, if it's the anode, that's where oxidation takes place. And that would mean that zinc would lose electrons. Losing electrons is oxidation, LEO. Losing electrons is oxidation. And so that becomes zinc 2 plus 2 electrons. So that means that zinc ions are produced at the zinc electrode. Obviously, copper solid is not being oxidized because copper is the cathode, and that's where things get reduced. So it would be the opposite process. Electrons always flow from the anode, which is zinc, to the cathode, which is copper. So that's got it the wrong way around. And SO4 2- is an anion, so it should migrate towards the anode. Anion migrates towards the anode, but this says it's migrating away from the zinc, which is the anode, so that is wrong as well. Okay. I feel like we missed 25. Did we miss 25? Go back. Yep, we missed 25. All right, so which of the following would be the cathode? And once again, this is where we have a power supply. So that means this is not a galvanic cell or voltaic cell. It is an electrolytic cell. Therefore, it is non-spontaneous. And the way you can tell which direction the electrons flow is by looking and saying electrons move away from negative and they move towards positive. And electrons move from the anode to the cathode in alphabetical order. And so we are going from the anode to the cathode. And I love how they throw in the ion here, because the anode and the cathode, they have to be like a stick of something. If it's not a metal, then it has to be like an inert electrode like carbon. So obviously the cathode is not copper 2+, because the electrode is the stick of something, not sulfate ion. It is the iron, because that's where the electrons are moving towards. Okay, that was 25. Did we hit 29? Nope, we did not hit 29. Or did we? Yes, we did. We did hit 29. Cross that out. 37. Which of the following half reactions is required for an electrolytic process needed to plate an iron automobile bumper with chromium? So we have an automobile bumper. This used to be more of the thing. Now bumpers are all plastic, but you used to have chrome bumpers on cars all the time when I was a kid. Okay, so there's our bumper, and it's made of iron, and we want chromium to plate onto it. So what that means is we need to take chromium, which is 3+, and we need it to gain 3 electrons and become a chromium 0 atom. So we need to, if we're plating it on, we need chromium 3+ to gain 3 electrons and become chromium solid, so that the thing is now plated with solid chromium. So that's going to be this one here. Okay. That was 37. By the way, is that bumper going to be the cathode or the anode? Is that going to be the cathode or is it going to be the anode? Yeah, it has to be the cathode because we are having reduction taking place there. So that's the cathode. In an electrolytic cell, anytime you want to electroplate something, whatever you want to electroplate is going to be the cathode. Whatever you want to electroplate is the cathode. Do you have a suggestion for what I should make the anode out of? What should I make the anode out of if I want to plate this iron bumper with chromium 3+, or sorry, chromium 0? Yes, I should make it out of chromium, because the nice thing is then that as the chromium 3+ in solution, you know, here's my solution. I know this is getting really ugly really fast. But as the chromium comes out of solution forming chromium 0, at the anode, you're going to have oxidation of chromium 0 into chromium 3+, which can then zip on over here and plate onto the bumper. Excellent. Okay. 37 is done. Where are we at? No 40s. Okay, so we're at 50. Who is the reducing agent? So if we are looking for a reducing agent, we are looking for the thing that gets oxidized. So who are my potential things? Probably carbon is one of them. Okay. And if I'm looking, I've got SO4 stays as SO4. So when a polyatomic ion stays as a polyatomic ion, it's not undergoing oxidation or reduction because you've got SO4 2- and it is still SO4 2-. So we're not looking at the SO4, we are looking at the carbon. And we're hardly ever going to, we won't be looking at alkali metals unless they are going from being positive to being neutral. And here it's an ion, so K is always positive. K can't be any charge other than positive when it's in a compound. So it's not K. So that leaves us with manganese. Okay, we have manganese and manganese. So let's take a look at carbon and see if carbon gets oxidized. Ooh, can you tell me without finding all the oxidation numbers? We have CO2 and we have, it's becoming H2 C2O4. We could find oxidation numbers or we could cheat. Oh, can I repeat the part about K? Yes, in a compound, your alkali ions are always +1. They're never any other charge when they are in a compound. The only time they change oxidation state is when they go from in a compound, so KCl, to being not in a compound, being an element, K solid plus Cl2 gas. Yes, because here K has a positive charge, chloride has a negative charge. Here K has a 0 charge and chlorine has a 0 charge. So unless you're doing either synthesis or decomposition with an alkali ion, they are not going to be undergoing oxidation or reduction. Okay, because within a compound, they will always just be +1. You can't have potassium 2+, for example, because remember, potassium has 1 electron on its valence shell. So if you've lost that 1 electron, now you've got a shell that is much closer to the nucleus, and it is very, very unlikely that you're going to lose an electron from that second shell. So you'll never end up with a K2+, because this is so much closer to the nucleus, it's being held much tighter, held more strongly. Did that sound okay for K? Yes, thanks. Excellent. Good, 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 good. Okay, so back to our CO2. I'm going to do that little thing where I've got my ratios. I've got 1 carbon to 2 oxygen. Here, I have 2 carbon to 4 oxygen, which is the same as 1 carbon to 2 oxygen. And the only difference between these compounds is that this one has hydrogen and this one has no hydrogen. So I have gone from having no hydrogen to having hydrogen. And when we add hydrogen on, that is reduction. This little cheat I actually got from biology, because there's a lot of this type of oxidation and reduction in biology. But of course, you could do it by finding the oxidation numbers. So if this was reduction, if CO2 underwent reduction, then it was not the reducing agent, because it got reduced. So it can't be the reducing agent, which means that it's not going to be anything else other than manganese. And you can check your manganese. You can say, okay, manganese, we have MnSO4. MnSO4, oh, that's messy. SO4, and our other one was KMnO4. KMnO4. And you have a polyatomic ion here, so you don't actually have to do anything fancy with the S. This is just -2, which means that manganese has to be 2+. So the oxidation number is 2+. Over here, we know that K is +1, and I know that MnO4, the whole thing, is -1, but I don't actually need to know that. I'm going to get rid of that because that just maybe complicates things. So I've got a K, I've got an Mn, and I got 4 O's. And so my K is +1, because alkali ions in a compound are always +1. Looks like an H. Let's change that up. Manganese is the one we're looking for. And 4, oxygen is always -2. And that's 0 overall. So we have -8 and +1 gives us -7. Mn -7 equals 0. So Mn is now +7. So we have gone from having Mn of 2 to Mn +2, +7. That oxidation number got bigger, so that was oxidation. And if you have been oxidized, then you are a reducing agent. So that's going to be our MnSO4 was our reducing agent. Phew. All right. That was number 50. Let's do 52. Fe2+ reacts spontaneously with, I'm just going to jot these down so I can look at them. I got I2COBr minus and Ag plus. So let's go to our data booklet. Oh, and it was Fe, yes, Fe2 plus, Fe2 plus. And my feeling is if this one was tricky, it's because Fe2 plus actually shows up on both sides because it can be going from Fe0 to Fe2 plus, or it can be going from Fe3 plus to Fe2 plus. So let's find all our Fe's. There is an Fe2 plus right there underneath the water. And my other Fe2 plus is down here maybe? No, up. Where's my Fe2 plus? There's my other Fe2 plus. Okay, so those are my two Fe2 pluses, and I want to know who is going to react with, let's see, we've got I2. Is I2 going to react with either of those? That's uphill, so that's a no. The other one is they're both oxidizing agents, or sorry, yes, oxidizing agents. So that's a no. Cobalt, CO. That one's uphill. And these two are on the same side, so that one doesn't work either. Cobalt's no good. So no to cobalt, no to iodine, I2, Br is up there. Oh, that does not look promising because that would require a huge uphill slope, and these two are on the same side. So that's a no. So that leaves us with only Ag plus. Let's hope for the best. Is Ag plus going to work for us? Here we have Ag plus. And we do have iron on that side, and so Ag plus will react with iron 2 plus, but iron 2 plus won't turn into iron solid, it will turn into iron 3 plus. Okay. So that was number 52. 56. 56. Which of the following redox reactions represents an electrolytic cell? If it is electrolytic, you know that it is non-spontaneous. Non-spawn. So we're looking for, let's see, we got copper 2 plus nickel. We got silver plus nickel. We got Hg 2 plus nickel, and we got Al 3 plus nickel. So in all cases, we're reacting things with solid nickel. Okay, back to our data booklet. Nickel, solid nickel, where is that? Aha, there it is. Solid nickel. Okay, and we were looking for copper 2 plus. That would be a spontaneous reaction. So that would not be an electrolytic cell, that would be a voltaic cell or a galvanic cell because it's spontaneous. Silver, oh, I happen to know that silver plus is way up there. So again, that's going to be a downhill slope. So that's spontaneous. Hg2 plus also up here somewhere. Yep. Okay, so it is not mercury, it is not silver plus, it is not Cu2 plus. I'm guessing it's aluminum then. Let's go see, aluminum should be down here somewhere. And indeed it is. There's aluminum. And so that would be a non-spontaneous process. So that's going to be an electrolytic cell. Okay, anything else in the 50s? No. All right. let us go then to 64. There we go. Okay, so we have some S2O8, 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 2 minus. We have some SO4, 2 minus. Some, I can do 58 for sure. Yeah, 58. Some Cu, 2 plus, and some Cu. Placed in a container. Which of the equations represents the spontaneous reaction? So we're either looking for SO4 or S2O8 reacting with metallic copper, or S2O8 or SO4 reacting with copper 2 plus. Okay. So the two S's reacting with the two Cus. So let's go see what's spontaneous. So S2O8, that's way up at the top. Okay. Here we have our S2O8. Were we looking for spontaneous? I think we were. That's looking really promising because it's way up at the top on the left-hand side, which means it goes downhill to just about everything. So let's see, would it be going downhill to copper 2 plus, or would it be going downhill to copper? And I would say that because our metals are usually on this side, there it is. There's our copper. Oh, I don't want that one. I want this one. Okay, so there's our copper. And so that's our spontaneous reaction. You can see that if we had chosen SO4, it wouldn't react with the copper. That would be a no because they're both reducing agents. It would not react spontaneously with copper 2 plus because that's an uphill battle. And S2O8 would not react with copper 2 plus because they are both on the same side. So that would be S2O8 reacts with copper solid. And we were popping on back to number 58. An aqueous solution contains sodium, nickel, zinc, and copper. Which ions can be extracted by electrolysis of the solution? Okay, so we have sodium, nickel, 2 plus, zinc, 2 plus, and copper, 2 plus, and this is an aqueous solution. When you hear aqueous and we're looking at electrolysis, we have to take into consideration H2O, okay? And because these would all be gaining electrons in their reaction, say that Na, that's our sodium, for example, that would be reduction. So we have to compare these 4 ions with water and say, are they going to be reduced favorably compared to water? Are they more spontaneous than water, or are they less spontaneous than the reduction of water? So, reduction of water, where are you? Reduction of water. So this gaining electrons is reduction. Here is my reduction of water. Okay. So we are going to compare that with nickel 2 plus and sodium way down there, and zinc 2 plus and copper 2 plus. Where are you? You're up high, up high. There we are. Copper 2 plus. Okay. We have copper, zinc, water. Oh, that's not zinc, that's nickel. nickel, zinc, and sodium. So copper is better at getting reduced than water. Because it's got a higher reduction potential. So it is better at getting reduced than water. Okay. Nickel is also better at getting reduced than water. It is negative 0.26, which is bigger than negative 0.41 volts. So nickel is also better at getting reduced than water. Both of those have a higher reduction potential than water. I'm going to skip zinc just for a moment because I'm not sure that, anyway, never mind. I'll tell you when we get there. We're going to go to sodium right this second. So sodium, negative 2.71. It's way worse at getting oxidized, or sorry, reduced than water. So we can say yes, nickel will get reduced even if water's present. Copper will get reduced even if water's present. Sodium will not get reduced because the water will be preferentially reduced instead of sodium. Now, when it comes to zinc, I did not stress this with you. I don't think I put it in the workbook. This overpotential, did we talk about the overpotential effect at all? I feel like we did not. We did. Okay. So I believe that you do not need the overpotential effect for the AP exam. It was in the videos. Okay. Okay, good. So you have heard of it. So the overpotential effect is this little bracket here, okay? And what happens is, as far as I'm concerned, the overpotential effect is like magic. I do not understand it. I've looked it up. It's never really stuck with me, okay? So I am going to assume that at this point in time, it will not stick with many of you either, like an actual explanation. So if you are looking in the regular chemistry exam and you see you're comparing water with any one of these things in here, those things will win. Okay, so if it's in the bracket, it wins against water. All right, same thing's gonna go if you had something in this bracket up here. So if you're saying, is water going to get preferentially oxidized, or is bromide going to get preferentially oxidized? Now, normally you would say, water, if it's getting oxidized, that's negative 0.82 volts. That's the Anode of oxidation. And for bromine, it would be, or bromide rather, Br minus, it would be negative 1.09. So normally you would say, it's going to be water is, it's less negative, so that would be have a better oxidation potential. However, because bromide is within that overpotential bracket, bromide is going to win, quote unquote. So bromide will be oxidized preferentially over water. So back to our question. Copper's better at getting reduced, nickel's better at getting reduced, and because of the overpotential magic, zinc is also better at getting reduced than water, even though it's below it on the chart. Okay, so I believe that will not be important on the AP exam, but it could come up on your regular test. I'll try not to put it on there because I think it's a little bit silly, but just at the high school level, I'm like, if I don't understand how to teach you why, then why are we bothering with it? So anyway, regardless, that was number 58, I believe. 58, yes, 58. where are you? 58. Oh, I'm crossing you out. There you are. And we did 60. So now we're looking at 64. Oh, we did 64. I just didn't cross it out. Let's do 66 then. 66. A student wants to determine the concentration of SN2 plus in a solution of, oh, that wasn't good. Where'd it go? There it is. So if I want to determine the concentration of SN2 plus, that's going to go in my flask. And I want to do it by a redox titration. So I want to figure out what's going to go in my burette. How do you know which side of the table? You pick which one you can get a spontaneous reaction with. So yes, SN2 plus, just like our iron 2 plus, we could choose things from different sides. So let's take a look. We have Br minus, Cr3 plus, Pb2 plus, and MnO4 minus. So let's go to here. And we're going to look up tin. And tin is on both sides of the table. So we have tin 2 plus here above the hydrogen gray line. And we have tin 2 plus here below the hydrogen green line. So we can choose anything as long as it gives us a spontaneous reaction. So we can choose anything from here, right, all the way up, because that will react spontaneously with tin when tin is being oxidized to tin 4 plus, or we can choose anything down below. Now, usually we don't end up using something down below because if you look, a lot of the things are solids. Can you imagine trying to drip solid zinc out of a burette, solid aluminum out of a burette? It doesn't work very well. So normally I'm guessing that we're looking for something that's going to react with this tin here because I've got lots of things that are nice, just ions, things that can be in solution. So we were looking for bromide. Oh, bromide's on the wrong side. Yes, too much writing on here. Let me get rid of all of that. There we go. Okay, so bromide. No, it's on the same side. And if it was reacting with the other one, it would not react because that would be non-spontaneous. Okay, so no to bromide. Chromium 3 plus. Ooh, hey, hang on. Is there a chromium 3? No, chromium 3 plus is here. So that's on the same side as this tin and it's below this one. So not chromium 3 plus unless it's up top somewhere. Is there a chromium 3 plus up here? Ooh, look, there's a chromium 3 plus. However, huge uphill, so that's non-spontaneous. You will not get a reaction, so that's no good. Lead 2 plus. I feel like lead should have 2 things as well, but maybe it doesn't, because lead comes in 2 and 4 plus varieties. But I don't see the other lead. So no, not lead, because we were looking at tin and saying, how about lead? And that's a no. And so the answer has to be MnO4 plus. MnO4 plus. But let's just double check, because there are MnO4 pluses all over the top of this table. So we got MnO4 plus here. We have, do we have MnO4 plus anywhere else we ought to do? I feel like we should do. There's another one there. Now, why do I have 2 of those? Either of them will work. Either of them would react spontaneously with tin. But what's the difference between those two reactions? The one at the top says MnO4 minus plus 8H plus 5 electrons. I'm not going to write the products because it's just too much trouble. The one at the bottom down here says MnO4 minus plus 2H2O plus 3E minus. And so the difference between these two is that the one that's up higher, we would have to specify acidified. Every once in a while, the pen goes crazy on me. It does just something really weird. Acidified MnO4 minus. Okay, otherwise we cannot use the one at the top of the table. This one, because it's just reacting with water, would be in neutral or basic solution. This was in one of the other packets, but could you use a spectrophotometer for colored gases? Well, you know what? I'm not going to put that on your test, and it's not going to be on the AP test, because in the AP test, we solely use the spectrophotometer for colored ions in aqueous solution. Ooh, my chat is enormous. I need to make that smaller again. There we go. Okay, and let's see if I missed anything in the chat. Oh, okay. Okay, good. Good. How are we doing? Are we like dying? Do we need to take a break, or do we just want to push through because we're almost done? Or, well, we're not almost done, but we're getting there. Are we good pushing through? Just get it out of the way. Or are you dying and would you like a 10-minute break to go to the bathroom or something? Ooh. If you don't care, I'll just keep going. Keep going. Okay. Eddie says keep going, so we'll keep going. If anyone objects, too bad. All right. I am recording this, by the way, so if you're like wanting to see any of it again later, I will post it up on our teams. All right, we were on 60 something, so now we're on 72. So we're doing 72 to 75. Okay, 72. Here we go. A solution of FeCl3, which really means Fe3+, reacts with copper. That's yes, that's spontaneous. While a solution of Fe2+, because that's really what this one is, FeCl2, does not react with copper. So this one is spontaneous. This is non-spontaneous. Okay, so what is the order of strength as oxidizing agents of Cu2+? Oh, this should say Fe2+, because otherwise it's Fe3+ and Fe3+. So that's a little typo there. My apologies. So, I mean, in theory, you could look this up on your table, but let's assume that you got this on an AP exam and they do not give you a reduction potential table. Don't think they do anyway. They used to, but I don't think they do anymore. I think they just give you the numbers that you need as you go. So we would take a look and we would say, I have Fe3+ plus 3 electrons. I'm just going to make my own little chart. Yes. And if that's going to be spontaneous with copper, that means copper has to be down below. Okay, which means that Cu2+ plus 2 electrons is like that. Okay, so that gives us a spontaneous reaction of iron 3+ with copper. And continuing, making my own chart, that also means that because Fe2+ does not react spontaneously with copper. That must be a non-spontaneous uphill battle. That means iron has to be here. So now if we're looking in terms of oxidizing agents, this is our strongest oxidizing agent because it's really good at getting reduced. And this guy is our weakest oxidizing agent because it's not as good at getting reduced. And so that means that in terms of oxidizing agents, it's going to be Fe3 plus first, and then Cu2 plus, and then Fe2 plus. All right. Titration. Okay. 10 milliliters of an oxalate salt. So here's our oxalate, and we have 10 milliliters of it. Is required to titrate 10 milliliters of KMnO4. Don't get freaked out by the fact that they just start tossing away the spectator ions. That just happens all the time. They assume that you know that K plus dissociates from MnO4 in solution, and so that KMnO4 is exactly the same as MnO4. Okay, and so this one we have 10 milliliters, but we also know that this is 0.1 molar. So when you do a titration, you're going to have one substance, which is your known substance. And in this case, that is our MnO4 minus, and we know that it is 0.1 molar, and we know that we have 10 milliliters. We're also going to always have an unknown substance, which I'm just going to call UNC, okay, for unknown. Unknown, which in this case is the C2O4, because it asks what is the concentration of the oxalate. So that is the C2O4 2 minus, and we don't know its concentration, but we do know that it is 10 milliliters. And so what you're going to do, please, please, please do not do this. I don't know, my grade 12s, my regular 12s have started using M1V1 equals M2V2, which is a dilution equation. It is not a titration equation. It generally, if people use this doing a titration, I feel like they don't really know what they're doing, okay? I think they're just slamming things into a formula and hoping for the best. Do not use this for a titration. I'm sorry I even mentioned it, but I got so many people using it this year. I feel like it's just going around somewhere or other. Someone got some resource or something, I don't know. Anyway, do not use it for a titration. That is for dilutions only, okay? I don't even like it for dilutions personally, but some people really like it for dilutions. Okay. What you're going to do, if I can stop this thing from hopping around, okay, there we go, is you are going to take your known substance, whatever you know about it, you're going to convert it into moles. It's always a three-step process. Moles of your known substance. You will convert that into moles of the unknown substance. So it's always going to be moles to moles. Okay, and in order to go from moles to moles, you use the mole ratio. This is stoichiometry, yes. And from there, you're just going to find whatever of your unknown you want, okay? You might need to do a conversion, you might need to do a division. In this case, we want to have molarity, which is equal to moles over liters. So once we know our moles of our unknown, we can put that right in there, and then we can divide by liters. All right, so let's do this. Our known substance, we have 10 milliliters. Do you guys mind working in millimoles? Can I work in millimoles? It's just nicer. I'll do it in millimoles, and then if you hate it, you can ask me to show you in moles. Okay, so I know that I have 10 milliliters of 0.1 mole per liter of MnO4 minus, that's our known substance. Okay. My liters will cancel out, leaving me with millimoles of MnO4. Be sure when you're doing a titration, if especially, I mean, obviously if it's multiple choice, nobody cares what work you show, but in a written response, always write the substance beside moles. Because you'll be changing substances. So if you just write moles, then I don't know what kind of moles you're talking about. So that's in any kind of stoichiometry, including titration. Okay, so we now have moles of MnO4. So we've gone from our known, and we found moles of our knowns. We've done that. And now we need to go to moles of our unknowns. So we need to convert from moles of MnO4 minus into moles of our unknown, and our unknown substance is the C2O4, C2O4, 2 minus, and our mole ratio there, back to our question, we have 5 C2O4 for every 2 MnO4. Okay, so 5 C2O4 for every 2 MnO4, and now our moles of MnO4 have canceled. And so at this point, we have millimoles of C2O4, and I'm just going to put an equal sign now and do that calculation. And so that's 10 times 0.1 times 5 divided by 2 is 2.5. And remember, my unit right now is millimoles of C2O4 2 minus. What did I want to know about the C2O4? I wanted to know the molarity. So concentration of C2O4 2 minus is equal to moles of C2O4 2 minus over the liters of C2O4 2 minus. So we have, or millimoles over milliliters. Ah, look at that, because my millis will cancel out. So I'm going to take my 2.5 millimoles of C2O4 2 minus divided by my milliliters, which was, I think there were 10. Yeah, 10 milliliters. 10 milliliters. And you get 2.5 divided by 10 is 0.25 molar C2O4 minus. All right. Would anyone like to see that again without the milli? Nobody is saying anything. So I'm going to move on. Yes, you would. Yes, you would like to see it. Okay, so let's do it again without the milli. So instead of 10 milliliters, we are going to start with 0.01 liters. Okay, so that's our liters times 0.1 moles of MnO4 minus per liter. So now we have moles of MnO4 times, and we're still going to use the same mole ratio, 5 moles of C2O4 2 minus divided by 2 moles MnO4 minus, which gives us 0.01 times 0.1 times 5 divided by 2 is 2.5 times 10 to the minus 3 moles of C2O4 2 minus. And you can see we've actually got the same thing here, 2.5 millimoles. Remember, milli is 10 to the negative 3, so we got 2.5 times 10 to the 3 negative moles of C2O4. So the calculation is basically exactly the same, but you've either got a 10 to the negative 3 or you've got a milli. And then you would do your concentration of C2O4, and instead of worrying about milli over milli, you would just do moles over liters. And so that's going to be 2.5 times 10 to the minus 3 moles, C2O4, 2 minus, divided by, and we had 10 milliliters, which is 0.01 liters. And so that gives us 0.25 molar. So same answer as before. Okay, whichever way you like doing it is fine. I kind of like milli because then I got numbers that don't have exponents all over them. Where did it all go? It jumped around again. But nothing wrong with changing it to moles. Nothing wrong at all. Okay, can we take a small break now? Yes, we could take a small break now. Should we break for 5 minutes, 10 minutes, 15 minutes? What would you like? 5, 10, 5, 5, 5, 5, 5, 5, 5. Let's make it 7 minutes, shall we? So let's break for 7 minutes. 7.5 minutes. Okay, so it is now 12:27, so that will be 12:34. Let's make it 12:35. Okay, so we will come back at 12:35. That'll allow us to use the washroom, stretch a little bit. Okay, 12:35. Hello and welcome back. So when last we left, we had just done a titration, and I believe that this one is going to be very, very similar. So once again, we're going to be starting with something which is our known, and then we're going to find moles of the known, moles of the unknown. So anytime you're doing a titration, in the middle, you've always got moles and moles. Okay, and then we're going to find whatever we need to know about our unknown. So what do we know things about in this question? Well, we know two things about the KMNO4. We know its volume and its molarity. That makes it a good choice for our known substance. So that is 22.3 milliliters and 0.10 molar KMNO4. And we know that we have our unknown. We're being asked for the concentration of the NB5+, and that's going to be in moles of NB5+ per liter of NB5+. And so we're finding moles of KMnO4 and then converting it into moles of NB5+. And we also know a little something about the NB5+. We know that it is contained in a volume of 10 milliliters. So we know that we have 10 milliliters here. Okay. If you guys don't know this already, of means times. Of means times. Of means times. So if you're given 22.3 milliliters of 0.10 moles per liter of the KMnO4, if you just substitute times for of, then your liters cancel out nicely and you are left with millimoles. I'll go through it again real quick with regular moles. Okay, and then we want to go from moles of one substance to moles of another substance, and that's going to use our mole ratio. And so we have to go up to the equation, find the moles of KMnO4 for the moles of NB5+. So KMnO4, and remember, KMnO4 just becomes MnO4, and we ignore the K+ because the K+ is a spectator ion. Okay, so we have a 2, oh, look, it's a 2:5 ratio again. So we've got 2 of those for every 5 NB. So 5 NB5+ to every 2 of those. So now all we have left is millimoles of NB5+. And we're going to put an equal sign at the end of that. So 22.3 times 0.1 times 5 divided by 2 is 5.575 moles NB5+. So the concentration of NB5+ is equal to 5.5. Oops, sorry, that's millimoles. That's the only thing I don't like about the whole millimoles is I usually forget to write the milli, and then it's like, oh, well, what was the point of that? So I got 5.575 millimoles of NB5+ over, and my volume of the NB5+ is 10 milliliters. My millis cancel out, and all I'm left with is moles per liter. So divide by 10 is just 0.5575 moles per liter, which is the same as molar. So that would be 0.56. Got to bring up the chat again. It's gone away. Chat. There we go. Okay. Just super, super quick, doing it without the milli. Hopping about. Why is it hopping? No hopping. Please, no hopping. Okay, so that was with the milli. Without the milli, we just convert our milliliters. 22.3 milliliters becomes 0.0223 liters times 0.1 moles of KMnO4 per liter. That gives us moles of KMnO4 times 5 moles of NB5+ for 2 moles of KMnO4. And if you chose to write just MnO4 minus instead of KMnO4, that would be totally fine. Either way, nobody's going to care because you can either put the spectator in there or leave it out. In this case, it doesn't matter. And for this one, you get 5.575 times 10 to the minus 3 moles of NB5+, and the concentration then of NB5+ is 5.575 times 10 to the minus 3 moles of NB5+ over 10 milliliters, which is 0.010 liters. And we get the same answer as we did before, 0.56 molar. Okay. Whew, titrations, you need to know how to do them. They come up in electrochemistry, they come up in solution chemistry, solubility, equilibrium chemistry, they come up in acids and bases. You need to be able to do these titration calculations absolutely cold. It should just not be something you even have to think about. Once you've written this test, if you want to get a little extra practice, just let me know. I have many titration problems I can send you to work with if you need to. Okay, that was 74. We are now on to 75. I don't know what happened to this page. Everything, I moved something by accident and it's all askew now, but that's okay. Which of the following best describes the overall reaction and standard cell to voltage in a lead acid storage battery? So this is like a car battery, or the lead acid batteries. And so we are given these half reactions here. The overall reaction. So if we were to do the overall reaction, we would need to take these two and add them up. But we also need to make sure that we have an oxidation and a reduction. So this is, we're going to have, oh, not sure if we already went over this, but number 38, I can for sure. Do the ions flow between the half cells, or is it only the ions in the salt bridge that go to the half cells? I will go over that in just a second. That's a good question. Number 38. Okay. Yeah, so this is our positive voltage here. So this is going to be our reduction. So it's going to go forward. This one is our lower voltage. So this one is going to go backwards, and that will be our oxidation. Okay, so I'm going to just, can I fit it on here? I can, excellent. So I have PbO2 plus 4H plus SO4 2 minus plus 2 electrons goes to PbSO4 plus 2 H2O. That's our reduction half reaction, our oxidation half reaction, writing it the correct way around. Pb plus SO4 2 minus goes to PbSO4 plus 2 electrons. So all we're doing is we just took this reaction up here and we wrote it backwards because it's the oxidation. So now we are going to add the two of these up, just like we did when we were writing full redox reactions, because that's what we are doing here. Our electrons cancel out. I don't see anything else that cancels out. And so we will have PbO2 plus Pb. We got that one, I got that one. I don't know why I'm not doing this in the order, but anyway, we got 4H plus. And we have two SO4 2 minuses because we've got one in each of those reactions. So plus 2 SO4 2 minus. So just looking at this, I'm thinking this looks like a good choice here. Yeah, I don't see another one that looks the same. So I don't even need to calculate the cell potential. And then that goes to 2 PbSO4 plus 2 H2O. But if I did need to calculate the cell potential, remember we have E naught of the cell. It's either going to be E naught of reduction at the cathode minus, oh my God, what a mess. Minus E naught of reduction at the anode. And if we do it that way, this is our cathode, this is our anode, and both of these guys here are reduction potentials. So that would be positive 1.69 volts minus negative 0.36 volts, which is positive 2.05 volts. Your other option, of course, you can say E naught of the cell is equal to E naught reduction at the cathode plus naught of oxidation at the anode. And if we do that, our cathode reduction is still plus 1.69 volts. But our anode, remember, this is our reduction potential for the forward reaction. And so if we're looking for the oxidation potential, the E naught of oxidation, it's the backwards reaction. So we change the sign. So that's going to be positive 0.36 volts plus positive 0.36 volts. And we still get positive 2.05 volts. Okay. All right, I will go back to number 38 in just a bit, but we're right in the middle of the 70s and there's like a whole string of them in a row and it just makes more sense to just keep going with them for the moment. Which of the following are produced at the anode and cathode during the electrolysis of aqueous magnesium iodide using carbon electrodes? What do we know about carbon electrodes? Carbon electrodes are, with an I, inert, which means unreactive, which means we do not need to worry about the carbon. So we are dealing with aqueous, so we have H2O as one of our things, and we have Mg2+, and we're also going to have H2O compared with our other thing, which is the I-. And the only thing magnesium can do is to gain electrons. So this would be our possible reductions. And H2O, the only thing I can do is to lose electrons, right? And it would become I plus 2 electrons. And if you're like, I don't know, how is she pulling this out of, nowhere? We'll go and we'll look at it on the chart, okay? And then that would be plus 2 electrons, whatever the heck is there, okay? So these would be our oxidations. So let's go look. We have I- and Mg2+. I- and Mg2+. So here is our chart here. Our Mg2+ is quite far down, I believe. Yes, it is. Okay. So Mg2+ is here. And so that we are looking at reduction. So let's compare our magnesium reduction with the reduction of water. And here is our water getting reduced, gaining some electrons. So who is better at getting reduced? Is it water or is it magnesium? Well, negative 0.41 is less negative than negative 2.37 volts. So water is better at getting reduced. So if we're looking at our two reductions, who's going to get reduced? It's going to be the water. And if it was a written response question, you could write down the voltages and say, because the reduction potential of water is 0.41, that's bigger than negative point, blah, 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 blah. Okay, but this is multiple choice. We don't have to do that. Our other substance we were looking at is the I-. And the only thing it can do is get oxidized, losing those electrons there. And so let's now look at water getting oxidized. So the oxidation potential of iodide is negative 0.54 volts because we changed the sign. And the oxidation potential of water is negative 0.82 volts because we changed the sign. So iodide is better at getting oxidized. So iodide is the winner, and it's not, and yeah, never mind. Babbling things now. So I minus is the one that gets oxidized. And so our products are going to be I2. And when water gets reduced, I need to look it up. I shouldn't, but I do. When water gets reduced, we get H2 plus 2OH minus. Okay, so don't be shy about looking that up. So our products are H2 plus 2OH minus. Those two electrons there. So what is produced at the cathode? Well, the cathode is where reduction takes place. Remember, C and R are both consonants. So reduction always takes place at the cathode, and oxidation always takes place at the anode. Those are both vowels. Okay, so at the cathode, we are going to get H2 and OH minus. So at the cathode, we're going to get H2. So that's going to be one of these two. OH minus, I guess they're just ignoring. And if we remember oxidation, who won the battle? It was I minus, so it's going to produce I2. That's at our anode, so it's going to be that one. So our answer is D. Consider the diagram to the right. Identify the cathode in the half reaction. So here we have an iron electrode on the right. And on the left-hand side, we have H2 gas and we have HCl. If we have HCl, you need to remember that HCl dissociates into H plus and Cl minus. Okay, all of your acids that start with H dissociate. Okay, so we are dealing with H2 and H plus. And over here on the right, we're dealing with Fe2 plus. Okay, there's our 2 there, so it's Fe2 plus and iron. So let's go look those up and decide which is our spontaneous reaction. We're looking for H2 and H plus, and we're looking for Fe2 plus and Fe. And how do I know that this thing is not reacting? Because, oh, it's gold. It's gold. Well, I guess we could look up gold as well, but I don't think anything happens there. Gold tends to be very unreactive, like platinum. Any of your really sort of those precious metals tend to be very unreactive. Their ions tend to be very reactive. So silver plus is very reactive, Au plus is very reactive, but the metals themselves tend to be non-reactive. But you could look it up anyway. Okay, data booklet. Okay, H and H2, there they are, right in the middle of the table. There's our H and H2. Fe solid and Fe2 plus is here. Okay, let's just satisfy our curiosity about gold. Au, there it is, way up there, which means that it's a very weak reducing agent, which means it doesn't get oxidized easily. So that's not going to be a spontaneous reaction with either the hydrogen or the iron. Okay, so now taking the gold out of the equation, we're looking at these two possibilities. So which is going to be our spontaneous reaction? It's going to be the one that has H plus as the reactant and Fe as the reactant. So we're looking at 2H plus 2 electrons, H2, that's going to be our reduction. And we're looking at Fe solid going to Fe2 plus 2 electrons. Those are going to be our products. That's our oxidation. What was the question asking us? I've forgotten. Ooh, identify the cathode half reaction. So our cathode is going to be the one where reduction is taking place. So that's going to be the one where the hydrogen is, because that's our reduction. So this is our cathode right here. And what's happening at the cathode is a reduction. Reduction always takes place at the cathode. And if you don't like the vowels and consonants, you can always remember anox, cared, cathode reduction, anox, cared. Okay. And if we're looking for that one, we're looking for reduction. There is our reduction reaction right there. Okay. Okay. 70. Where did we get to? Okay. I think we're done with the 70s. So let's bop back to number 38. Where'd you go? 38. Which of the following is the function performed by the salt bridge in an electrochemical cell? It's not a non-electrolyte, that's a silly answer. It allows the solution in each of the half cells to become electrically charged. Electrically charged is a bad thing according to nature, because if you get like a bunch of negatives all hanging out together, they're going to repel each other. That is unstable. So that's not what a salt bridge is doing. It's actually trying to prevent the solution in each of the half cells from becoming electrically charged. It provides a pathway for the migration of ions from one half cell to the other. So that is going to be, and I think the question around this one was, is it only the ions from the salt bridge, or is it the ions from like the half cells? Yes, it is all the ions. So if you had, do I have a picture of a half cell here? Oh, there's one. Okay. So we have our lead and we have our aluminum. Lead is the cathode. Aluminum is the anode, I think. Double check. Oh. Aluminum is below lead. Yeah, okay, good. Okay, so if we were looking at this, we would have K plus ions, and they would migrate towards the cathode. However, over here, you've got aluminum ions, and they would also be like, oh, you know what? Some of the Ks are leaving the salt bridge. So that's leaving the salt bridge slightly negatively charged. And so the aluminum is going to kind of flow in here as well. It's going to take a while. It's not going to get over to the other side very quickly. So it's, you know, it's going to spend some time here and then here, and it's, yeah. So and the nitrate, this nitrate will come up to join that nitrate and migrate towards the anode. Did that answer your question on number 38? Yes, excellent. And because we're going backwards, let's go look at number 4, because we never did that one. Hello, number 4. There we go. Oh, not that. There we go. Up. Oh yeah, we're omitting number 4 because it's a gray question. Number 4 is gray, so we're going to omit it. We'll do it after equilibrium. And number 6, a student has been directed to oxidize iron to Fe2+, but not to Fe3+. So our choices are, we have zinc, we have tin, silver, and fluoride. And I want to take Fe to Fe2+, but not Fe3+. Okay, data booklet. Okay. So I want to take iron. There's iron. And I want it to go that way to Fe2+, but I do not want Fe2 plus to go to Fe3 plus. Where's that one? La, 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 la. Come on, you're somewhere. There it is. Okay, so I do not want this. No. Okay, so I want something that will react with iron, which is down here, but not with iron 2 plus, because I want iron to go to iron 2 plus, but I don't want it to turn into iron 3 plus. So I want something in this section here, because these will be spontaneous with the iron going to iron 2 plus, but they will not be spontaneous with iron 2 plus going to iron 3 plus. So out of our choices, we have zinc. Well, that doesn't work because that doesn't oxidize either of them. We have tin 2 plus. Tin 2 plus is there. So that would work because it would oxidize the iron, but not to iron 2 plus, but not iron 2 plus to iron 3 plus. So tin is looking like the good choice. Silver is not going to work because I think it does both. Yeah, silver's up here. Excuse me. So silver would do both. It would oxidize iron 2 plus to iron 3 plus. That's a spontaneous reaction downhill, and silver is downhill to that one as well. Let's get rid of that because that's super messy. And then F minus, I think F minus is just on the wrong side. Excuse me. Yeah, F minus is just on the wrong side. Okay. So that was number 6. Now we're going to 81. Excuse me. 81. Scrolling. Keep scrolling. Sorry. You guys don't know Rawhide, do you? Anyone seen the Blues Brothers? Okay, so 80 we are skipping because it is a gray question. We'll learn that later. 81. The same amount of electricity, same moles of electrons, is used to carry out. Ooh. I'm a little concerned. No, probably it's okay. I'm just a little bit weirded out by the fact that I've got copper 1 here. We don't usually have copper 1, but I'm going to go with copper 1. The masses of palladium and copper were compared. Okay. Which of the following is true about the mass of palladium produced comparing grams of palladium to grams of copper? So I'm going to grab my molar masses while I'm here. Copper has a molar mass of 63.5 grams per mole. Palladium has a molar mass of 106.4 grams per mole. Now, if we have the same number of moles of electrons, oh, I wrote PB, I meant PD, 2 plus. PD requires 2 moles of electrons. D, 2 plus, needs 2 moles of electrons to reduce to D, whereas copper, which is +1 according to this, only needs 1 mole of electrons to reduce to copper solid. So if we had the same amount of electricity, so let's just say that we had 1 mole of electrons, because why not? We can pick any number we want. So let's just say 1 mole of electrons. So if I have 1 mole of electrons, this is a 1-to-1 relationship. I'm going to end up with 1 mole of copper. With the palladium, it requires 2 moles of electrons, so it's a 2-to-1 ratio. So 1 mole of electrons would give me only 0.5 moles of palladium. Now, you could have chosen 2 moles of electrons as your starting point. The deal is you're going to get half as much palladium as copper. So we get half as much palladium as copper. And well, copper is more than half the molar mass of palladium. So it's not going to be a nice half or twice as much or even the same, even without rummaging through my brain and figuring out which one's bigger and which one's smaller. I can immediately eliminate these ones because they're not tidy. This is not a tidy 1-to-2 relationship at all, this one here. Okay. Are they going to be approximately the same? No, because again, it's not a tidy. So I'm going to guess that it's 84% times the mass. Let's chug our little numbers through and see what we get. So if we have 0.5 moles of palladium, that's going to be what's 106.4 divided by 2 is 53.2 grams of palladium. And if we have 1 mole of copper, that's 63.5 grams of copper. And so palladium, 53.2 grams of palladium divided by 63.5 grams of copper is 63.5, 83.7, yay, 83.7. I multiplied by 100 and I didn't write it down, but that's okay. It's a multiple choice. Okie dokie. So whenever you're given things with moles of electrons, you're going to be writing half reactions so that your electrons are there. And if they don't give you a number of moles, you can just make one up because it's the same amount. You could set everything to 200 moles of electrons, 3 moles of electrons, but I like 1 or 2 because those are nice small numbers to work with. All right, that was number 81. Okay, 83. Consider the following spontaneous reactions. Which is the strongest oxidizing agent? Since these are all spontaneous, what that means is that these guys over here must have been stronger at their job, and these guys over here must have been weaker at their job. Now, what the heck does that mean? Well, in our first reaction, cadmium is going from 2+ to 0, and so it has been reduced, therefore it is the oxidizing agent. Okay. And that means that NP is the reducing agent. Now, if we were to look at the reverse reaction, so if we were going backwards, then cadmium would be going from 0 to 2+, which means it was getting oxidized, which means it's the reducing agent, and that means that NP3+ is the oxidizing agent. Now, if you are a strong oxidizing agent, you are really good at oxidizing the other guy. So cadmium 2+ is successful at taking 2 electrons from NP. NP is not good enough to take 2 electrons from the cadmium and go backwards. This reaction goes forwards, so it does not go backwards. So whichever side has the stronger oxidizing agent, it's going to turn into the weaker reducing agent. So we know that when we compare oxidizing agents in this reaction, CD2+ is stronger than NP3+, because CD2+ pushes this reaction forward. NP3+ does not manage to make that reaction go backwards. Okay, so CD2+ is above NP3+. Same logic. What we're going to do is we're going to identify our oxidizing agents and our reducing agents. So CD is going from 0 up to 2+ in our second reaction. So it has been oxidized. So it is the reducing agent, which means its partner must be the oxidizing agent. And whoever was the reducing agent is going to turn into an oxidizing agent. And whoever was the oxidizing agent is going to turn into a reducing agent. Okay. And so we are going to be now looking at who is stronger. Well, this reaction proceeds in the forwards direction. So who's good at doing their job? These guys here are good at doing their job. So who is the stronger oxidizing agent? We're comparing palladium to cadmium, and palladium pushed the reaction forward. Cadmium did not push the reaction backwards. So palladium is stronger than cadmium. We're going to put palladium above cadmium. And now finally, in our last one, NP goes from 3+ to 0. So it has been reduced. So that would be our oxidizing agent. And because it was the oxidizing agent on the other side, the NP is going to be the NP0 is going to be the reducing agent. We also have, if this is our oxidizing agent, the CE has to be the reducing agent. And its partner on the other side, CE3+, has to be the oxidizing agent. Because this is going forwards, that means that NP is stronger and CE3+ is weaker. And so CE3+ is weaker than NP3+. So in terms of ranking them, we would go, this is our strongest oxidizing agent, and this is our weakest oxidizing agent. And so who is the strongest of them all? Palladium. That was 83. Moving on to 86. An aqueous solution. Aqueous means you need to look at water because it is electrolysis. Anytime you have electrolysis and aqueous, you must consider water. Okay, and we have copper electrodes. So I have in my beaker, I have Cr3+, no, not 3 plus, 2 plus. I have Cl minus, I have water, and I have copper electrodes. So in my beaker, sometimes I like to draw a beaker because it just helps me think what I've actually got here. I've got copper, I've got Cr2 plus, and I've got chloride, and I've got water, and I've got, I don't know, battery here. Positive, negative, okay. What is going to happen to the mass of each electrode and the chromium in solution? So chromium 2 plus is going to get reduced if it reacts at all to chromium. And we have to compare it with water getting reduced. So this is our reductions, possible reductions. That's going to be at the cathode, of course, because reduction takes place at the cathode. Cl minus, well, if you think, is Cl minus something that can gain electrons? No, right? You can't end up with Cl2 minus, so we're just going to not write that one down. And is it possible for our other substance, copper, to also get reduced? Does it make sense to have copper 2 minus? No, it doesn't. That's a goofy thing. Have you ever seen a copper 2 minus? No. So you can look through all your substances, but sort of it makes sense if you've got things that are positive, they can undergo reduction. Things that are negative can undergo oxidation. So let's look at our possible oxidation reactions at the anode. And so we're going to look at things that are negative because negative things can lose electrons. So we have Cl minus, and it's going to become Cl2 plus 2 electrons. And we need 2 of those. And if you don't know that, it's okay. Go and look it up. Like go look up Cl on your data booklet. We will do that in just a moment. And of course, water is always an option. And remember, we also have Cu, and could Cu lose electrons? Is it possible to end up with losing electrons there? Yes, because we could end up with Cu2 plus, and there we go. Okay. So reductions, chromium and water. Let's see who's chromium and water. Cr2 plus. Cr2 plus, is it Cr2 plus? Oh, and Cr2 plus. Oh, Cr2 plus could also lose an electron and become Cr3 plus. Oh my goodness, that's so tricky. So Cr2 plus is another one of those multivalent metals that could go either way. It could get reduced to chromium 0 or oxidized to chromium 3 plus. So let's go look. Let's look at our possible reductions. What's it asking us for? Mass, chromium. Okay. Chromium and water. That one's easy. Let's look that one up. Cr2 plus. Cr2 plus. There's water getting reduced. There is chromium. Where's chromium getting reduced? There's chromium 3 plus getting reduced. Where's chromium 2 plus? I do not see it. Maybe it's up further. Chromium 2 plus. Hello, are you here? It's not there. Okay. Well, then I'm going to assume, I guess I'm going to assume it doesn't get reduced. This question's making me unhappy. And I know it's from a bit of a dodgy source, so we're going to find out if it's actually okay. So let's go look at our reductions then, or it's not our reductions, our oxidations. Oh my God, why are we all the way back at the beginning? Oh no, 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 no. Ah, yeah. Where'd we go? 3. Oh, 86. So we had possible oxidations at the anode. We have Cl minus, H2O, copper, and chromium 2 plus. Okay. Cl minus. Is anyone else dying? Like, because I feel like my brain is dying right now. Oh, and my battery is running low. I gotta plug this sucker in. Okay, hang on. Hang on. My question to you is, do you want to keep going right now? Or would you like to, because we no longer have the assessments, we could do this at a second session, or we can just push through. What do you want to do? Keep going, or maybe do a session on Wednesday or something. How much is there left? Second session, push through. How much is there left? There is 1, 2, 3, 4, 5, 6, 7, 8 questions. I'm dying. I'm away on Wednesday. We push through. How about Tuesday? How about tomorrow? Are we free tomorrow? Because I'm dying. I don't know about the rest of you, but my brain is like lost it. Could we do, you're also away tomorrow. You can just watch the video. Okay. You have basketball practice at 11. What if we did it at, let's see. I have a thing at 12:30 tomorrow. You just watch the recording. Okay, I have a thing at 12:30, but if we did it at 11, we've done more questions today. We should be able to do it at 11 and finish by 12:30 at the latest, I would think. Yes, are we good with that? Tomorrow at 11? And then if you have a question that you didn't get answered, yeah, okay. Okay, so tomorrow at 11, let's do that. That way I won't lose my mind and maybe you won't lose yours either, I hope. Okay, so I'll see you guys tomorrow at 11. We'll finish this question then. All right, take care.
Thank you.
You're welcome.
Bye.
Have a great day.
Thank you.
All right, recording, stop recording. Where is it? Or stop recording. Or end.